Many thanks, Adrian, for very nice talk. Okay, so we are open for questions. So please. Okay, Riddhi has a question. Riddhi, please go ahead.
About this point in the real stars and planets.
Yeah.
So in this real system, there would also be magnetic field, right?
That's right. Yeah. Yeah. So that's also not incorporated in the theory yet.
Okay.
So in Stephenson's paper, he included the effects of magnetic fields as well, but I think those scaling laws haven't been as well tested as the rotating ones. But you're right, the magnetic fields could play a role here as well.
Right, and that could have another direction, right? Which is different from the...
That's right. So that's another way in which actually the effects of rotation could be inhibited through, you can break the Taylor-Proudman balance essentially by adding in a magnetic field. So that's another thing that would come into the theory and affect the transport laws.
Okay, another small question. So you showed that the heat conduction is suppressed along the direction of the rotation, right? The temperature gradient becomes small as you increase, as you get it more rapidly rotating.
So the temperature gradient's larger to carry the same heat flux.
Right.
So, yeah.
So could this, I know in neutral fluids, as you increase the speed of rotation, it gets more two-dimensionalized, right? Does this happen because of this? I mean, this is also neutral fluid. I'm just saying.
Sorry. Could you repeat that? You're saying that as you increase the rotation rate, you become more two-dimensional. Is that what you're saying?
Right.
Yeah.
So is this happening for the same reason here?
Yeah, it's related to this. So it's the fact that as you go to rapid rotation, the rotation inhibits variation along the rotation axis. So you can get, when convection, you always have to have some 3D motion. You have to have some variation in the Z direction. So it can't be purely 2D in the XY plane. But the motions, you're right, that there can be the motions of the convective flows, with the exception of the fact you need a Z direction to drive them. I guess they are more strongly dominated by the 2D motions.
Got it.
It isn't a purely 2D system because we need the Z direction to drive convection.
Okay.
Yeah, that makes sense.
That's it. Thank you.
Okay, some other questions, please.
Yeah, hi Adrian, this is Abhishek. Can you hear me?
Hi, yeah.
So very, very interesting talk. I was reminded of my supervisor's comments, Peter Davidson's comments, that most simulations, they don't dimensionalize by the viscosity. And that means it's a slippery slope to interpret the results that we obtain. So I quite like the fact that you are solving the dimensional equations, but I can't help thinking about some non-dimensional numbers. So my question is regarding the Rossby number regime. So what regime is relevant in your simulations? And in particular, because Keith Julian in his PRL paper said that this real number to the power 3/2 law, that basically breaks at local Rossby number of the order 1.
Yes.
So in the context of that, have you thought about those aspects?
Yes. So I guess the aspect we haven't looked at is related to boundary layers, which I know they discussed quite a lot.
Yes, that was going to be my next question.
So we're always actually in the regime of small Rossby number here. So this is the convective velocities in units of the flux.
Right.
So it's similar to, but not exactly the same as the convective Rossby number in these units. So there's an order 1, so to exactly do this is not exactly straightforward, but you can think of these numbers as being convective Rossby numbers. So I think they're actually, the convective Rossby number in the usual way of calculating it is smaller than this, I believe, slightly. But so these are always smaller than 1, so it's always in the rapidly rotating regime according to that.
Right.
Well, you can see that actually, if you normalize the convective velocities by the mixing length scaling, then this is 1 in the units of the simulation.
Right.
So this is indicating when you've got numbers less than 1 here, then these are in the convective Rossby numbers less than 1 regime.
And these are Rossby number based on the box length.
That's right.
So to talk about the local Rossby number, that would be they would be even smaller.
Yeah, that's right. Yeah, that's right. So particularly for large rotation rates, the box size in the horizontal and the modes in the horizontal are really small. So in that case, the Rossby number is even smaller. That's much smaller. Yeah, that's right.
And you said there's this K-perp law, which is based on the viscosity, that is not expected to hold in any real situations, and that's what you see in your simulations as well. So what is the K-perp law? Maybe I missed that.
Yeah.
What is the K-perp law that you found from your simulations? If it doesn't depend on, so it does depend on the rotation rate. It does depend on the H. What else? Okay.
Yeah, so the K-perp depends on, it does depend on the rotation rate and on the angle with the rotation vector for the latitude.
Yeah, okay.
It does depend on the buoyancy frequency as well. So it depends really on the convective Rossby number, essentially, that appears in here. But in this diffusion-free regime, and the thing I didn't write here because I used the non-dimensional numbers, obviously it has 1/h factor here, but
right, yes.
H is 1. So yeah, it just depends on omega z.
Okay, omega z and H, yes. Okay, interesting. So buoyancy frequency, I can't help think about the stratified rotating case. So perhaps something like this can be done for the stratified rotating case also, and especially at non-other latitudes, because not much has been done on.
You do mean stably stratified rotating?
Yeah, stably stratified, because the outer part of the, for example, the core of the Earth, that is thought to be stably stratified. So something like this could be done even for that, I guess.
I'm not sure. Possibly some ideas, yeah. So I guess in that case we don't have. Well,
we would expect some inertial gravity waves, for example, to be present.
I guess there it's more like wave turbulence,
right?
Might be different from. So this isn't as wave turbulence as such.
Yeah,
this is the dynamics of unstable convective modes, but maybe some ideas would carry over into that problem.
Idea would carry over. Okay.
Yeah, possibly, yeah. I haven't looked at that problem in detail, so I'm not sure.
Okay. Yeah. Thanks, Adrian.
Okay, thanks.
Okay, anyone else? Okay, Adrian, I have a couple of questions.
Sure.
This 3/2 and 1/2, 1/5, sorry, 3/5, 1/5.
Yeah.
They all remind me of Bolzano-Volkoff scaling of stably stratified flows.
Right.
Right. So of course you have convection here. I mean, this is a totally different system in many ways, but rotation is probably making it somewhat. I mean, so for the Navier-Stokes equation, for the momentum equation, what is balancing what? The nonlinear term is balancing the buoyancy term for
this balance, yeah. So if you want to think of it in terms of balancing terms, then I guess you can, in the rapidly rotating regime, think of it's related to how one of the ways in which this type of argument is derived. It's essentially a balance between the rotation Coriolis term, buoyancy forces, and the nonlinear term, essentially.
I see. Okay.
So these are of comparable magnitude in the equation.
Okay. So what is the energy spectrum? I mean, that's something which I look at all the time. I think you have enough resolution, so you can look at the spectrum. I mean, does it go? Yeah.
So this is it's not the energy spectrum; it's the heat flux spectrum multiplied by K. So if you were to plot the, I believe, like I have looked at the energy spectrum at some point, like the vertical, like UZ spectrum, and also the heat flux spectrum. And essentially, it's in terms of the horizontal wave number, you have a -5/3, something that's consistent with -5/3.
I see.
So, this one is -2/3 because I multiplied by K. But if you didn't do that, it would be -5/3.
I see.
In terms of the horizontal wave number, in the turbulent cascade, and then I guess that would be modified obviously by diffusion down here. But yeah, this is consistent with a -5/3 in terms of the usual way of plotting things.
Okay. So one more comment. One more observation, which I think is somewhat different than what Riddhi was trying to say. So in one of the slides, you have shown that UZ is of the order of U-perp, right?
Yes, that's right. So this is based on the heuristic derivation of mixing-link theory.
That's right.
Yeah, so you can get that actually it depends on which mode you're talking about in the spectrum. So for the modes that have scales with the horizontal scale of order this one, then you can show from the linearized equations that these are comparable.
I see. Okay.
So it depends on which mode you're talking about, though.
So it is not quasi 2D because, it's not in the sense of strength of the velocity field. It is not quasi 2D, but you need enough vertical velocity for the heat to be transported upward. Is that?
Yeah, I think so. Yeah. So for the dominant modes, the vertical and horizontal velocity components are comparable. But if you go to, this depends on scale, because it does depend on scale, but for the ones that dominate the heat transport, it does seem as if you have comparable vertical and horizontal components.
That's right. Okay, so this is what I wanted to ask. So I would like to see, I mean, of course, I'll download your paper and see whether can one make some similar arguments at Volyanov-Bukov so they're all 1/5, 3/5, and so on. It would be interesting to see that. So that's wanted to say. Any other
I'm not sure if those arguments been used in this context. I'm not sure, but yeah, I'd be interested to hear about that.
Yeah. So anyone else has a question? Okay, I guess not. So you can stop here today.